let's look at chords and arcs of circles and various things associated. So a chord is simply a segment between 2 points on a circle. So here EC is going to be a chord. Of course, we already know what to call AC and AE. Those are radii. Remember, radius and its plural radii, that can refer to the number, which is the how far each point on the circle is from the center. But it's also used to talk about any one of those segments that connects a point on the circle to the center. So we got 2 radii and a chord here. And the first point, and this really incorporates essentially the information of theorems 12.4, 12.5, 12.6, and basically 12.7. And that's that circles are the same in all directions. And that should not be surprising. That's kind of what makes them circles, that anywhere from the center, anywhere you look, they look the same. And so, for example, if I happen to know that a certain angle in this exact position with an 83-degree angle, that's a Greek beta, by the way, which is what GeoGebra chose for that letter. If that corresponds to a chord length of 5.43 on this circle, then if I rotate it around, as long as I keep the angle the same, the chord length is going to be the same. Or if I know the chord lengths are the same, the angles are going to be the same. It doesn't matter what direction this is all happening in. There's going to be the same link between the chord length and the angle. Now, if I change the angle, if I make that angle smaller, the chord length is going to get smaller for sure. So now it's about a 30-degree angle, and that chord length is a bit smaller. Well, let me see if I can bring that on screen. And so smaller angles are going to correspond to smaller chords, and bigger angles, bigger angles are going to correspond to bigger chords until I get to a whole diameter. But the point right now is simply that what doesn't affect it is which direction that's happening in the circle. So if I have 2 chords with the same angle, I'm going to have the same length and vice versa. So that's good to know. Probably the least obvious version of that is something I'll show you in just a minute. Let me pause for a second. So now I've souped up the picture a little bit. I've got AD, and that is the closest distance between the center and the chord. That is not coincidentally 2 other things. That is, D is exactly the midpoint of E and C. Hopefully that's pretty plausible. You can prove it. I'm not going to worry about that. But if you start out on the edge of the circle and you're going over to E here, it's exactly halfway in between that you're going to be closest to the center. And that's also exactly where the perpendicular bisector, that's this line GADF, exactly where the perpendicular bisector goes through. So that right angle, the fact that these 2 are congruent, so that D is the midpoint, and the fact that D is the closest point on that chord to A, those are all always linked. And just like I was talking about, if I rotate the whole picture, I'm creating a bunch of chords, a bunch of options for CE, and I'm rotating them around, and you'll notice that CE is still not changing. The angle CAE is not changing, and the other things that's not changing is that distance to the center. So all of those are linked. If I have 2 chords like this and this, or 3 or 4 or 5 or 6, however many chords I create, if they all have that 2.66 distance from the center, they're all going to be congruent. They're all just rotated versions of each other. So the pictures in the book are a little different, but I wanted to show you this kind of dynamic version of it, where one way to think about it is I just rotate this whole picture, it doesn't change. Now, what changes, again, is if I make that C and E close together and make that angle smaller, this is the angle up here. I didn't have it marked here, but it's right here, 30.5 degrees. That's that angle CAE. Then, of course, the chord's going to get smaller, and the middle is going to get further away from the center of the circle. Eventually, it's going to get really close to the circle itself. When that chord gets close to a diameter, the chord's getting really, really close to the center, and if it is a diameter, it's going to pass through the center. Okay, so that's cool. And like I said, the other fact that's really nice here is that if I know D is special because it's the closest point, or because it's the midpoint of the chord, or because this angle is a right angle. Those are all equivalent to each other. If I know one of those facts, I know all of those facts. So that's cool. That really gets most of the theorems in this section. You should look and see how the book does them. But that really summarizes most of the theorems that we've got. It's basically that this picture isn't misleading. That everything that looks nice, like the fact that these are congruent, that D is a midpoint, that this is perpendicular, it's the perpendicular bisector, that D is the closest point to A on the segment, and that it doesn't matter if we rotate it, that picture is going to be the same. All of those things are exactly like they look. So let me do a little numerical problem. This is a little bit like one of the examples in the book. I realized I was doing a lot of things verbally I should probably write down. That congruent arcs give congruent chords. Congruent chords, vice versa, give congruent arcs. Well, actually, arcs slash angles. Because if you have the same arc on a circle, you're going to have the same angle. Congruent chords. All of these are just that when I look at two things that look like they're rotates of each other on the circle, they are, and they're everything about them that's interesting is congruent. And the midpoint of a chord is the closest point on that chord to the center, and the perpendicular bisector is a diameter, and vice versa. If I pass a diameter through a chord, let's say, through the midpoint of a chord, it will be perpendicular. Basically, like I said, everything about this picture, if you know one thing, you know everything. Now, I've included one more thing. So now we're going to make a little numerical problem. So suppose I know the diameter of the circle is 7.1. So that's illustrated. It happens to be IH here. That happens to be a diameter. Let's say it's 7.1. Let's say centimeters. Let's put some units in. And I know the chord length is 4.71 centimeters. I'd like to know how long. We know that we saw with the dynamical version, we know that the chord length relates to how far D is, that minimum distance of the chord from the center. And of course, it's going to depend on the circle. If the circle gets bigger, everything is going to get scaled up. So it's going to be something about the relationship about the chord length and the diameter. So how long is AD? In other words, how far is the chord from the center? And the cool thing is, so that's a question really, I could have just drawn just the diameter and the chord. I probably should have started out with that. Even if I just had just the chord and the diameter, I could ask this question. But I know I can draw this other stuff. In particular, I can draw this perpendicular bisector, GF, going through that chord. And I know that's a right angle, so that's key. So I know that angle ADE is 90 degrees, perpendicular. And remember, it's a circle. That's so easy to forget. The definition of a circle is that I, E, F, C, H, G, all those points are equidistant from A. In particular, I know AE is a radius. Oh, they didn't give me the radius. Well, yeah, sure we did, because the diameter is 7.1 centimeters, so that's half. That turns out to be 3.55 centimeters. Okay, and now to the rescue, our favorite Greek guy, Pythagoras. That's going to tell us, because ADE is a right triangle, and that's going to tell us that AD squared plus DE, well, let me put it in. Oh yeah, and I forgot to say one more. I know DE. I kind of need two sides of the right triangle, don't I? But I know DE because this is not some random point. That's the midpoint here. And I know that DE is half of 4.71. Oh my gosh, 4.71 over 2. That is 2.355 centimeters. Okay. So now my mystery length squared plus 2.355 squared is 3.55 squared. Oops, I need an equals. 3.55 squared. So that's going to be the difference. Let's go ahead and calculate that. That's 7.0, where was it? 0565. And that's not what I wanted. Sorry about that. And so AD is the square root of that. This is getting really familiar. Manipulating Pythagoras. And so that's about 2.656. Yeah, let's call it 2.866. Okay, let's check it. We've got this nice computer algebra thing here. Let's see. A, D, yay, 2.66. Right on.